Ja, bei Facebook musst du immer höllisch aufpassen.
Hello everybody and welcome to Fun with Flags. Oh, wrong format, sorry. Of course, welcome to our pop-up series, and today's topic will be Inside the Machine, Roasterphysics. But what is physics? Physics comes from the old ancient Greek word physica, and it is the science of natural things. But luckily today I did not bring Sheldon Cooper, but I brought my dear colleague Sebastian, and maybe you can say some words about you, and since when are you at Probat, what are you doing, and yeah, just say a few words about yourself.
Yeah, my name is Sebastian Tück. I've been with Probat for, it's 13 years actually now. I was joined in 2009. I've never seen another company. I started here out as a technical draftsman, and then went on to get my bachelor's degree and my master's degree, and then was asked by our CTO, Mr. Kotzorowski, if I want to get a PhD, and that's been what I've been doing for the past 6 years, I think it is. Time just flew. And yeah, I worked on the physics behind the roasting process and tried to put the entire science of roasting into numbers, and yeah, I think we got pretty far with that.
This is actually so cool. I'm really looking so forward to that, because what we were talking about today is what I do, just in terms of what actually feels kind of logical for myself, but I never, of course, could say it with any physical background, because this is just not what I do. So therefore, I'm really looking much forward, and also for the audience, if there is questions, of course, there's Jens also here with us, handling the chat. So whenever there's a question coming into your mind, just send it to the chat, and we'll be happy to answer it. And yeah, I would say, let's just get started. I will just take a seat.
Sure, go ahead.
And listen to you.
So I'd say first we get over the basic symbols of what we're all talking about today. So the first one's going to be what is called the heat flux, which is energy which is transferred to, let's say, the bean or the roaster wall or whatever, and it's not continuous, it's over time, that's why it's a flux. And it's in terms of watts, which probably everybody has heard already, which is energy per time. The next one we're going to be talking about is going to be the volumetric flux, which is again a flux, so it's changing over time, which is measured in cubic meters per second. And it's actually, everybody of you knows that, it's how much air is flowing through your roaster per time. So how much air does your fan move? And we measure this as a so-called volumetric flux. Mm-hmm. Another part is going to be the pressure then. I don't think I have to emphasize much about that. It's how hard is the air pushing against something. Like, you can feel it if you blow on your arm, you're going to feel the pressure of the air. And that's going to be measured in Pascal, who used to be a mathematician, and that's why we call it that.
I'm very happy for this explanation already, because, as I said, roasting okay, well, but physics no.
It's also going to be Newton per square meter, and Newton also was a mathematician, so. And the final thing is going to be, we're going to denote it W here to not get confused with anything. It's our velocity, which is basically just our volumetric flux divided by an area. So if you think about the volumetric flux and you want to know how much of it is going through, let's say, a pipe, mm-hmm. You divide it by the area of the pipe, and you're going to be at the velocity.
Which is already one of the very important things when it comes to setting up your roaster, and of course the pipe after the roaster.
Yeah.
Pretty cool.
And actually there's a small pipe from your burner to your roaster. And in general, your drum is a pipe filled with particles. So yeah, we have a lot of pipes in roasting.
Okay.
And now we want to get into the really hard parts, which is going to be thermodynamics. Sounds really bad. And if you're first semester engineering class, it is really bad. But it gets, actually, it's not that bad if you get the hang of it. And we're going to try to make it really, really simple.
Okay, cool.
And that's why we're going to start with the drawing. Let's draw your roaster wall. Technical draftsman, but please don't judge me too hard on this.
So this what you're drawing now is actually the surrounding of our roaster,
Yes,
right? Where
exactly.
the drum is inside then.
And the drum's going to be somewhere right here with your rod in the middle.
Okay.
So what I want to talk about today first is conduction. How do we move heat across solid materials, like from one roaster wall to the other? How do we move it if we touch a table? Those kinds of things. And the way it is we have a temperature on the outside and we have a hotter temperature on the inside. So what's going to happen is we're going to have, so just for explanation, this is going to be metal, insulation, metal, air. Also air. So we're going to have an outside temperature, and then we're going to have a temperature inside the metal, which is going to be pretty steep because, as we know, if you touch metal, it absorbs heat very, very fast. Then we're going to have insulation, which is not as steep, and then again metal, which is steep. So this is our temperature profile. Is going to be inside your roaster. Important side note for a stationary process. Let's say you've been heating your roaster for 45 minutes. That's about what the temperature is going to look like inside your roaster. If the temperatures in and outside the roaster are changing, then it's going to look a little different, but let's keep it simple today because else we're going to write equations you never want to see.
Yeah, so actually this would be changed if I come into my roastery, I start my burner and I wait for my roaster to heat up. So I should give it enough time so that we have the heat being able to move from material to material.
Exactly. From in the beginning, like if you come into your roaster, it would look something like this.
Yeah.
Because inside temperature is outside temperature.
Yeah.
So we got to raise it up. And we can't do without some equations. So I'm going to write this down, how this is working. And this is going to be, the heat flux is going to be equal to heat transfer coefficient times an area, which would be the inside area or the outside area of your roaster, times a temperature difference, which is inside minus outside, divided by the thickness. And this, that's very small. Let's make that on the bigger one. This would be the thickness. And this lambda, this heat transfer coefficient, is going to determine the steepness, so the slope of the temperature gradient inside the material.
So also here again, from my logical understanding, because you also say we always need a certain amount of time to transfer the heat, it would also, in your eyes, make more sense to heat it up over a certain amount of time to be sure that all the material is being nicely heated through and through, and not just fire it up and then just get started, right?
Yeah, that's what I was talking about in the beginning. This is stationary, so you reach the point of equilibrium, things don't move much anymore. If you just give it in the beginning and you're going to go in with a couple 100 degrees and just go for like a quarter of an hour, then we get into those equations I don't want to show you. Then things get really complicated. And the problem with that is you can't judge anymore. If you have a stationary profile and you want to start roasting, things are somewhat predictable.
Yeah.
If you didn't do that, things are going to go downstream very fast.
Yeah, and also here we do have things again which are probably not that predictable, like for example, moisture content in the bean, size of the bean, temperature of the bean. This is all stuff we more or less know, but also here this is always just a more or less, so we kind of want to keep it stable at some point.
You want to reach some equilibrium because that's how nature intended it. I'm just going to write, this is convection. It's energy moved in solid materials. So, but as you all know, this is not the main thing of a roaster. That's not how a roaster typically works. We want to have conduction, which is move heat with air. And this is a different form of energy transfer. And it's, I'm first going to draw it. We have this part here, and then we get to the inside temperature. This is 5. And we have it on the outside, which is going to be TA, so ambient temperature. So you see there's a little part right here that is not linear. And that things there become a little complicated. It's because air moves, and then there's going to be some part which behaves like the conduction we talked about, and then there's going to be turbulent parts, which is the air is moving and it's mixing, and particles with energy are going from left to right, and that's why this is unstable. The equation for this, I'm also going to write down. Oh, I'm sorry, I said convection. This is conduction. And basically, as you already see, we have two main ways with our convection to transfer more heat. We can either, actually there's three ways, but we don't have much influence on the area because you can't just increase your roaster. But then you can increase the temperature difference, which is what all of you have done a million times. Just ramp up that burner, just give it more. Increase the temperature going inside the roaster, and that's going to increase your heat flux. You're going to transfer more heat towards your coffee bean. And the other part is this heat transfer coefficient again. It's we call it alpha. In English, it's sometimes denoted H. Also heat transfer coefficient. And this is mainly concerned with the velocity of the air. There are two forms of convection. The one is the so-called forced convection, which is what we do. You put a fan there and you move air. The air is forced to move. It doesn't have any means of staying stable. And the other one is natural convection. And in a roaster, we have both. On the inside, we have forced convection. We have a fan which blows the air across the inner walls and transfer a lot of heat. On the outside, we do not have this. We have natural convection, which is your roaster is a little bit warmer than the ambient temperature, which leads to a difference in the density of the air, which starts the air to move close to the roaster. And that also creates a current, an airflow, which then in turn leads to small amounts of alpha, which then again lead to different temperatures. And that's two of the three ones we have. The last one is not as important, but I don't want to leave it unchecked, which is going to be radiation. Radiation is electromagnetic energy transfer, so it's transferred without any media of that type of sort. It's more like a wave kind of thing. And you can immediately see the difference. Compared to the others, it's to the fourth power. So the bigger the difference is, this term here shoots up really fast if you have a really big difference. But in terms of electromagnetic power, all we do here is not that big. So this part is normally going to be in the range of 10% of your heat transfer.
Yeah.
Most of your heat transfer is going to be convection.
But also, of course, with the convection, when we say we have two different ways, we can have either the air that we move, make it hotter, or we move it faster.
Yes, exactly.
And then sometimes people do it in combination.
Yes.
Is there, I'm quite sure, there is a formula that could give you the right amount of how hot it needs to be and how fast it needs to be to bring more or less energy to the product. But you have to always see both in combination, right?
Exactly. You need to know the airflow. It's not explicitly listed here, but this alpha is a function, as we as mathematicians say. The higher the velocity of the air is going to be, the higher alpha is going to be. And actually, we prepared a video for this, which you should all see now. It's we have a certain amount of temperature coming in and a certain amount of velocity, and you're going to see how this. You should see the temperature right now, and you see vortices behind the coffee beans, and they're a lot cooler than the incoming air. And it works both ways. So the hot air is going to heat up the coffee bean, and at the same time the coffee bean cools down the current, because nature always tries to strive for equilibrium. So we want to get to the point where the beans have the same temperature as the air. That's what nature is just striving for.
Okay.
And the formula you talked about, that's the other one we have prepared. There's another, there's a 3D graph we have which shows the velocity versus the temperature, and you're going to see the higher the velocity is going to be, the higher your transferred energy is going to be, and also the higher the temperature difference. It's temperature difference. I think it says delta T right there, so it's a little triangle if you don't know what delta is. That's just this term here in the parentheses, the difference between the temperatures.
But of course, this all has certain boundaries. That means when I come into my roastery and I heat up my roaster, I of course want to keep it at a certain point so that my material won't get too hot, because otherwise I could probably have myself been led to burning spots on the bean. So this is also what I don't want, right?
Exactly. If you overheat, you can have burning spots on your beans, and also you could damage your roaster, because if you heat up a material like metal on the inside, it's going to stretch out. And if you do this really fast, it's not going to stretch out the same everywhere, which could lead to the welds breaking, or the material just from spreading and contracting and spreading and contracting, developing some cracks. Yeah. So you want to go gentle in general. Your roaster's not going to break if you every once in a while
this would have
heat
been
it
my
up.
next question.
No, it happens over time. But if you do it every day, all the time, it's going to damage your roaster. Yeah.
So also here, from my logical understanding, it makes of course more sense to just allow the machine more time, heat it up more gentle, step by step, until I have the right temperature. Maybe overheat my dropping point to make sure that I have the right amount of heat inside, but then also kind of slowly drop it again before I drop my beans. Because when I understand correctly, my beans will be at disturbing point already, as they are cold and they're dropping into that hot area.
Well, another point we need to look at is if you're heating up over, let's say you decide on Monday to heat up for Friday, that's going to be a lot of energy waste. Is this going to be perfect? Yes, absolutely. But it's a lot of energy wasted. So everybody has to find for their own roaster, for their environment, the own right heating time. But it's always good to, your roaster best. We can do math, but your roaster. Find the point where you're heated all the way through, but have an inside temperature which is going to be right for your beans. Yeah. And this is probably not for every roast. This doesn't have to be the same heating time. It could be less, or you need more heating time for different batches. If you want to be faster, maybe go a little higher. If you want to be slower, maybe go a little lower.
Yeah, and then also here, of course, it will make a difference if I use my first batch and I think, oh, okay, I heat up my drum and my material quite well, and I drop my beans, and then I do the same with probably the fourth or fifth batch of the day. This will already have an influence, because the heat has been transferred differently to the material. Exactly.
The roasting itself will also have an impact on all those parameters again, which is not easily predictable.
And of course, it will make a difference if I put 5 or 12 kilo in a P5 or P12, or only use probably 3 kilo, because then I have less product.
Absolutely.
Okay, pretty cool.
So that's one part of heat, of the thermodynamics. That's all the equations we're going to do for that. The next thing we need to talk about is how do you influence those parameters with your roaster. So we talked about mainly you have two chances, which is alter your alpha or alter your temperature difference. And first we need to talk about pressure loss. Every part of your machine has something which is called a pressure loss. And I'm going to write for fluid. We're now in fluid dynamics, so we just changed branches, if you will. Pressure loss is going to be the drop in pressure. That's why it's a delta P. It's not an absolute pressure. It's a difference. It's going to be rho is the density of the air. So how much kilograms per cubic meter, times the velocity squared. It's halved. Why? Don't worry about it. And then you have something that's called a zeta, which is the pressure loss coefficient. Okay. And every single part of your roaster, let's For example, you all know at the back of your drum there's going to be like a perforated plate or some kind of mesh. This mesh is going to have one of those coefficients. And if you think about it now, so how does the pressure drop change? Well, obviously, if this is going to be a constant, we don't play around with our air density because we're at the same temperature. Only a change in temperature or pressure could change this. So if you increase the airspeed, you're going to have a higher pressure drop. So there's a very special case in your roaster where we have a device which controls this, and that's your slide gate in the back. So I'm going to attempt to draw one.
Yes.
It's going to look, I think it's something like this. It's going to stick in a little bit. Then we're going to have a point 1 and a point 2. What you're actually doing when you're pushing this in or pulling it out is you're changing the zeta value of it. So if we draw a graph, which is going to be the zeta value over, I'm going to call it a distance, how far is it in? It's going to look something like this. Then we're going to have maybe 0.1s here, and this is 0.2. And this is how you can influence the pressure drop of your roaster, and that's one way to increase it. And we use this to calibrate your roaster for your environment.
So it mainly has to do also with how long is my pipe afterwards, how far am I going through a room. And then for me, in logic, this is how I understand it, the more I push it in, the smaller my diameter gets, the less...
The air speed is going to increase, and that's going to lose, then there's more drag, and you lose more energy to this. Because if you're air and you're coming here, you get pushed down here, and you're going to do something like this behind, and this is called drag, and
because I only have a small way where the air can pass through. Exactly. When I open it more, I have more space where the air can pass through, and it has more space to actually move.
Yeah, exactly that.
Yeah.
So that's how we influence it with a slide gate.
If there is no other way to influence it, because this is actually with the small roasters what we don't really want people to do, because usually it's really hard to set it back to the position where it has been before. But therefore, of course, we came with the solution of having our fan speed that we can move. And this will be having more or less the same influence, right? Just in a more controlled way.
Yes. I'm going to get to fans in a little bit. I just want to show something else first. So we have all parts of your roasters would all have zeta values. Also, a pipe is going to have a zeta value, which is going to be dependent on the diameter and the length of the pipe. So, which you talked about, the chimney. If you have a very, very long chimney, it's going to have a lot of pressure drop. And if you have a short one, it won't. And if we sum all this up, there's going to be a so-called a curve, which is going to look something like this. It's the pressure loss across the volumetric flow rate. And we talked about that the velocity, as it gets higher, we square it. So the faster we get, the more pressure loss we have. We're just putting this in terms of volumetric flux now, because then the area doesn't matter. And it's going to look like this. This is one possible curve. And this is going to be our point 1. Slide gate at point 1 for different variations of the volumetric flux. Now we push it in more, it's going to look something like this. We increased the resistance with the slide gate, so we're going to have more pressure loss at the same velocity. So now we get to the fans. So how do we overcome this pressure loss, which is some form of energy? So what we're going to do is we need to provide this energy, which we do with a fan. And a fan curve looks something For radial fans, they look like this. Something like this. And then there's going to be the point where they connect. And this is the point where your roaster is operating at. So we can draw a line down here and one to the side. So with this slide gate, we can control how much air is flowing through your roaster at any given point. If we slide it more in, we're going to wander up the curve up to this point and have less volumetric flow because we increased the resistance. We now need to invest more power to move it, which is more pressure drop. So you see, you can switch around how much air is flowing through your roaster by just moving a slide gate, but it's very, very costly. You waste energy when you do this. So obviously we don't want this. We don't want to waste energy. And this is the way they did it in the 60s and 70s and 80s because energy was crazy cheap. But now we're in an age where energy is not cheap anymore, especially right now. So we need more efficient solutions for that. And the solution is a frequency converter. So we don't move the curve with a slide gate, we move the fan curve. Mm-hmm. We reduce the frequency, which reduces the revolutions. And what happens then is, I'm going to get a different color because I'm running
just
out
pick
here.
Green from your blue, whatever. Just short question to the people behind the camera. Is everything good to see or perfect?
So let's say, I think the standard value for your fans is 65%.
Yeah, this is where we put it in the beginning and then we can play up and down to move more or less air through. Exactly.
Exactly. So let's say we want less airflow. Mm-hmm. What's happening if we put it, let's say to maybe like 30, the curve looks like this. Put it right here. So we get, for setting 1 of our slide gate, we get this point and this point as connections. And as you can see, we also reduced the flow through our roaster. Mm-hmm. But this time at much less pressure loss. So we saved a lot of energy in doing this.
Yeah.
We can also go the other way, which would be increasing the fan speed, which would put us on a higher level here, and we would use more energy, but still less energy than changing the slide gate.
Yeah, but this also needs to be seen in combination with the burner, because otherwise, if I move too much air too fast through the system, which is not hot enough, then I lose temperature inside, and I probably even cool my beans, which I don't want.
The way a burner works is you have a certain setting of burnt gases. And you're going to burn that, and the flame's going to burn at about 1,800 degrees Celsius. So we need cool air with that, because nobody wants to roast their coffee beans at 1,800 degrees, because it's going to be the shortest roasting time ever, and it's going to taste horrible. So we mix it with cool air. Mm-hmm. So if you do this, the cool air is provided by your fan, by the way, so by your exhaust fan. Yeah. That pulls in the air.
It pulls in the air from the room. Mm-hmm.
Exactly. If you increase or decrease this velocity, the fan speed, you're still going to have the same amount of hot gases from the burner, but you're going to have more or less cool air, which is going to increase or decrease your supply temperature. Yeah. So unless you have it controlled, I think, which is an option, then the controller would keep your supply temperature stable, but it's not standard. Then your temperature is going to rise or fall.
And also here, this does not happen very often, but we do have sometimes roasters being set up in, let's say, a different outer condition area where they have probably the roasters on a higher level. And then, of course, the air has a different way to transport the energy. And then this also can help to have the change in between, so that we have more or less the same amount of heat being transferred, even though the air can probably not transport that amount of heat, right?
Exactly.
Okay.
If you let's go to the extremes. Maybe you're a roaster in the high Alps. You want to roast on 3,000 meters above sea level.
Yes, please.
And then you're going to have I'm going to draw another fan curve. It's going to be delta P over V dot. And normally our curve looks somewhat like this, I said.
Mm-hmm. But
now our curve is going to look something like this. Let's take another color so we know. So there is there's less pressure which can be provided.
Mm-hmm.
So things get a little more complicated now. It all has to do with the density of the air. Up in 3,000 meters, it's going to be a lot less. But the way the fans are composed is they always carry the same volume. So they're going to be at the same point, but they are going to have less density. So the W is going to be the same, but the rho, which is this part here, is going to be less.
Mm-hmm.
That's why the delta P is going to change. And that's most of the reason why you can't compare roasting profiles all over the world, because everything can be the same, but your surroundings are not.
Yeah. Yeah.
Also, the same thing happens if your outside temperature changes. Let's say here we have like 20 degrees, but if you're somewhere else, there might be 40 degrees outside, which is going to lead to the same result.
Does humidity also have an impact on this? Or
Not
is that
really.
something that you just can keep out? Because sometimes just thinking of some countries in Asia, Singapore, for example, what they have high temperature and high amount of humidity. And then, of course, the settings have to be different.
I've never seen a roaster which has been composed differently because of humidity, because the process of burning gas itself produces high levels of water vapor. So this is much more than the air we put in.
Mm-hmm.
It just overshadows it.
Okay, cool.
Okay.
Good to know.
So it seems that people are still following.
Okay.
Because we got a question from, I think it's Martin from Switzerland. And he asked, when he heats up the machine, would it be recommendable to reduce airflow going through the drum during the heat up process?
No.
No.
Airflow as fast as possible.
Okay.
Because the heat transfer coefficient is going to be the best at its highest setting. It's better to play around with the temperature difference. Okay. So go fast, and it's going to be fine.
If you would reduce it, would that mean yeah, I would say so. If my air is really hot and I don't move it through the drum quick enough, that I actually expose the heat to then my drum material and heat up my drum material too much?
No.
No.
No, because our drums are double-walled. It doesn't make big of a difference.
I suppose you would rather heat up the area around the heating oven. If we don't take the air from there.
Could that be the problem for the melted cups that we sometimes see?
I'm not aware of that problem.
Yeah, because sometimes you get some weird pictures from some burner, and I do know that there's some plastic cover on top, and we have seen those things, they have just been melted away.
If there's not enough airflow,
yeah,
that could be it.
Then
Then
it's just way too hot and that thing melts. Okay,
yeah.
Just keep that in mind too. Okay. Mm-hmm.
Yes, and actually I think we also prepared another picture regarding this, because I can only draw in 2D, and we have another one in 3D, which is, I think it's the velocity. What is it? No, it's the fan speed against the exhaust flap, and you can see the higher you push the fan speed, you're going to increase your flow, and the more you open your gate. 100% means 100% open, maybe just so people know. So 100% fan speed, the gate wide open is going to be the most air that's ever going to move through your roaster. Just you've seen it. So you're moving on a three-dimensional plane in your head, you just didn't know it.
Are we then coming close to the problem that if we have a very small bean, which is very light because it does not contain that much moisture anymore, that it could just be sucked out to the Jeff collector?
Yes.
Okay.
There's a certain limit to how much air you can put through your roaster.
Yeah.
For drum roasters, this is. For industrial machinery, there's ways we can mitigate that. But if there's too much airflow and the beans are light, you're just going to find them in your cyclone.
Yeah. Okay, then we need to either lower the slide gate or just lower the fan speed so that
lower the. Please don't move your slide gate. Move your fan speed.
Yeah, this is also what we always tell our customers. Once you found the right position for the slide gate, just don't touch it anymore.
If you move this and you don't find the perfect spot again, all your profiles that you ever made are going to be different. So if you have a frequency converter, use that.
Yeah. And also here, using the frequency converter, using the burner, playing around with batch sizes. This is actually something you should do one by one, because otherwise you're going to mess up with all your great formulas, right?
Well, as an engineer, you have one variable, you change it, you wait and see what happens. That's what I would say you do. Just change one variable at a time, see what happens. Unless you're like some kind of supermind and you can see what happens on both variables at the same time and you're moving on the three-dimensional plane we just showed you in your head. If you can do that, wow, please email us. We would like to get to know you.
That would be amazing.
We probably have a job for you.
Yeah, I know I can. So this is why I'm usually just changing one thing at a time. Or also here, just trying to... Yeah, but this more or less comes from experience, because I have seen what happens before. I said that before. I cannot explain it with any physical correlation. I just know, oh yeah, this has happened before when I did this, and then I just do it in a different way or just don't do it at all. But
something that also makes it more difficult is if you change one variable, the change is not going to be instant. It's going to take a little while because the air needs to be pushed, everything needs to settle in, all the parts need to acknowledge, oh wow, the temperature is different, or the speed is different now, and the system needs to go back to equilibrium. And it's not happening in milliseconds. It takes a little while to see the effect, and especially heat transfer takes time. You cannot instantly heat something.
Yeah, we saw that with the beans. So we always have that cool air which is coming, so it needs time. This is why time is so important to transport the energy actually to the medium that we want to heat up, in our case, the beans then. It's
not possible to, as everybody knows, it's not possible to do, let's say, a 3-minute roast and have the bean entirely roasted through. It's physically impossible.
Mm-hmm. And also here, the importance of our shovel system again, something that comes in my mind, because we can do all of this, but still our beans, they are moved in the same mechanical way, of course, unless I start playing around with my drum speed, which again has, I'm not only guessing,
implications,
but
yeah. And it's going to have implications you probably didn't think about, because if you start playing with a drum speed, one thing is your beans are starting differently, but also the velocity between your air and your beans is changing because they're thrown slower. So you just change your alpha, and that's probably not even what you wanted. And if we look at a drum, maybe I can draw this here. Normally the beans are something like this. That's how there's going to be a little bit that's rolling here, and most of them are going to be thrown.
Yeah.
And in the extreme, if you put it too high, they're all going to be up on the walls, which is going to look something like this. Then you're centrifuging, so this is going to be beans.
Yeah, then they're just sticking to the wall of the drum.
You're centrifuging your beans, and there's going to be virtually no convective heat transfer. You're just doing it all by conduction and radiation. It's going to take forever, and it's going to probably taste horrible. And the other extreme is there's going to be no flying beans anymore. So this pile is going to get bigger, and your beans are just rolling around, which again, you have no convection anymore. Your heat transfer is going to be way slower.
This happens when I overload, and also when I change my drum speed, right?
Yes. So the two parameters to get to this is different batch sizes and different rotation speeds. So we invested a lot of time to find the perfect drum speed, so maybe stick with that.
Okay. And also, the reason why I get completely different aroma is because the air that I'm actually using is just passing through the middle without actually having a great impact on the beans. And we say the impact in terms of aroma development comes from the hot air as it's nicely surrounding all the time the beans, which in this case is not happening.
Actually, you can think of air as a driver on the street. You're always going to take the road where it's not congested. You're going to take the easiest and fastest road. Air does the exact same thing. There's a lot of beans. I'm not going to go there. There's nothing right there. Let's go above the beans. It's simpler. It's easier.
Yeah.
And in that kind of way, you want to block the way of the air as much as you can, so you have as much convective heat transfer as you can.
So you force the air to go through the beans and give the energy to the bean.
That's why there's a certain optimality between the drum speed and the filling. And
So also here, it's very important. This is what we always say. If we say it's a 5 kilo machine, fill 5 kilo. If we say it's a 12 kilo machine, you can easily put 12 kilo. Of course, you can also put less if you want to. Always having in mind that this will have an impact on how your bean will be moved around and what will be happening with the airflow. And then, of course, you can also adjust this. And this is then when people always come and ask, so is there some kind of formula? If I just put half, do I lower my burner to also 50%? And do I slow down? This would be too easy, right?
Yeah, no. There is a formula, but you all don't want to see it. Something you need to keep in mind is we design our machines. If we say it's a P5, it's designed for 5 kilogram batches.
Yeah.
Everything is optimized for 5 kilogram batches. If you get away from that, yeah, it's going to work. Absolutely. But it's going to be a lot less efficient. And you're also businessmen. You waste money at that point.
Yeah.
And it makes sense if you want some special profile and
you want to roast really fast or something like that.
Exactly, you need something really fast. You can't make it with 5 kilograms. Yeah, but that's a business decision you just made. You want that profile because it's the best for the bean. Cool. It's going to be more expensive because you need more gas. That's a business decision. It's not a decision from a physics standpoint. It's one way to do it.
Pretty cool.
Due to efficiency, we have another question from Martin.
Yeah.
And he's wondering whether a high airflow wouldn't result in unnecessary energy losses, because the material also needs time to absorb the heat somehow, and material means both material and coffee beans. So if we just pass them too quickly, then is there enough time to transfer the energy from the beans to the material, so our coffee beans?
It's actually, the question is more complicated than it sounds. Yes, there is too much.
Okay, the answer will be given later.
No, it's going to be fine. Yeah. There is an optimal point there's always an optimal point to transfer energy. But as a rule of thumb, more airflow is normally more efficient than more heat. But yes, there is a point where you have too much airflow, because let's go back to extremes. If you have your fan set to all there is, and you also have your burner set to all there is, are you going to have crazy amounts of heat transfer? Yes, but you're also going to have crazy amounts of wasted energy out your chimney. So it probably makes sense to either lower your temperature and have maybe even lower than you thought. You can normally get away with, if you decrease this part, the delta T, and at the same time increase the alpha, you just save gas. And I'm not sure how it is now, but in Germany right now, electricity is a lot cheaper than gas.
So rather saving gas and go higher on the electricity, have the
yeah, normally that's more efficient.
Yeah.
But not for all the times, it's just a rule of thumb.
Yeah, for me, in my head, I always thought when my air is too hot and I don't have enough time to give it to the bean, I just suck it out without having used it.
Exactly, but the heat transfer to the bean is going to have been better.
Okay.
You're going to have transferred more heat to the bean, but you also lost more energy out your chimney. So that's also something you need to keep in mind.
Yeah, so you have to find the right level where you get enough energy to your bean and
Exactly.
not just throw it out the chimney unused.
One thing you need to think about is you can have the same amount of energy transferred by just moving those two values. If you move this up down by 10% and this up by 10%, it's the same. It didn't change. Your roast is going to be exactly the same.
Yeah, because you change the two variables at the same time, one up, one down, and then the result will be the same.
Exactly.
Yeah.
But the really complicated part is this is not velocity. So you cannot say you increase your velocity by 10% and decrease your temperature by 10%. This in itself is very complicated.
Okay, then don't get started. Not today. Maybe another time.
Alpha, just so you have an idea, the bean size has an impact on alpha. And how far the beans are apart also has an impact on alpha.
Okay, yeah, this might then again still be interesting because this is what is changing all the time when roasting the coffee.
Exactly.
Small beans, big beans, dense beans, whatsoever. And this is, I think, also what people struggle with because they try to put all this in very strict numbers and in very strict formulas, which might be possible if you think very complicated, but also here, for me, as just standing in front of the machine, it also is kind of a gut feeling because when you know that you have a more dense bean, you need more time or more energy to heat it up. It kind of seems logical. But then, of course, on the other hand, yeah.
That's the artisanship about it. Because I spent 6 years of my life putting all this into numbers, and I can confirm it works. But the problem is, it takes you 6 years, and I still don't know everything by heart.
Yeah.
And as people are going to tell you, I'm a horrible, horrible roaster. You don't want to drink my coffee. You really don't.
So maybe we should start working together, and I use the knowledge from roasting, and we combine it, and then we just see how it goes.
Yeah. So.
But if we come up with a formula, this will be.
Well, I have it. You just don't want to see it. There's just too many parameters.
Yeah. Obviously.
And that's also the beauty of it, because if it was easy, then everybody would do it, but it's not.
Yeah. Yeah, and this is also what, besides of making it the science, it's also, for me, coffee roasting is still art, because
yes.
when you write it down and when you try to explain it to me, at a certain point I have to say, oh yeah, that makes sense. And then at another point I say, okay, you kind of just lost me here, and I just think of what would make sense to me in terms of how would I roast that. And I think the combination of the two is what makes it so fascinating, because you can explain it all with physics, and then of course you have people who just give it a try. But if you give it a try, you waste coffee, you waste energy, and then probably you still don't come out with a good coffee. So having some of the basic physics knowledge, just, yeah, it makes completely sense. This is.
Yeah, and if you think about it, we talked a lot about the roaster here, but exactly this happens for your bean, because you have a coffee bean that's we just sliced through the middle of it, and it's going to be very hot on the outside, and there's going to be a temperature gradient from the out to the inside. So if you roast it really aggressively, you're going to be way overdone on the outside, but you didn't even start in the bean.
Yeah, and inside it's
under
roasted. Yeah.
This is nothing. It's absolutely the same as this. It's just further complicated because there's water in the bean, which is going to evaporate, which you all know is the drying phase.
Yeah. And then, of course, when we start with this, we have to say that then we have also coffees which are more dense, where it actually just from nature it takes more time for the energy to go to the inside and then starts to go back to the outside and get the whole process starting.
And if we want to put this back to math, a Robusta coffee just has higher heat transfer coefficient values.
Okay, but this is something for the next masterclass.
Yes, please.
Because we are running somehow out of time. I don't know whether you checked the boxes.
If there are no more questions.
There's another question, that's why I'm asking. So he's asking whether we do have a proposal or a tip how to avoid that the first 2 to 3 batches are different compared to the other ones. So is there an ideal way to heat up your roaster? You mentioned, okay, that it's depending from your roaster, what type of roaster you're using, whether it's a P5, P12, P25, whatever. But do we have a recommendation? What do we have? What do roasters have to do to be as stable as possible from batch 1 or 2 on?
So from my point of view, take some time heating up, and it's going to be a little bit of try and error. If you realize your first batch is always too fast, heat up slower. If you realize you're too slow, heat up faster. There's going to be an optimum you can find, but you need to find it yourself. I don't know if I'm spoiling now, and maybe I get in trouble for this, but we're working on something for you that makes it easier.
Okay. And once you've found it, you could easily make a recipe or a profile from this heat up process, and then you can recall it.
Yes.
Yeah.
One by one every
This is what actually I always say. What I recommend is heating up at least 40 minutes up to an hour. Just give it enough time so that, but sometimes you just don't have the time. And then I also got the question sometimes from customers, they were asking me if it would make sense to heat up the roaster with some material inside, not necessarily beans, probably some cherry pits, if that would help to kind of spread the energy more evenly. But also here, I think it does not really have an impact, because what you do is you have the cold material, and this will always be different when you start really with cold machine or when it's already warmed up.
Actually, I would say from a physics standpoint, it would harm, because there is more material which now needs to be heated up.
Yeah.
And the average temperature of the air is going to be a little bit lower than if you had nothing, so nothing is preferable.
Yeah. But I also, this is a question which comes very often, and I think that the only way is just heat it up in the best way ever, no matter how long it is or how much energy you use. Yes, it's not energy saving, this is for sure, but it at least gives you a hint on how your batches will be, or you just know that your first batch is always that different, with the same coffee, with the same outside conditions, with the same whatsoever settings, and then use this. But I think there's...
Maybe a good tip is, if you look at your, I don't know if every shop roaster has this, but if there's an exhaust thermocouple, if this settles in over, let's say 5 minutes, and there was no change, you're probably done heating up.
Yeah. You just need to make sure that you don't overgo the 250 inside the drum.
Yes.
Yeah, cool. If there's no more questions in the chat, I would say this might be enough for our first physics session, but I'm actually hoping that it will not be the last, because this is just so super interesting in terms of understanding why things are happening. We do know that they are happening, and we kind of make our way around to understand how, but if you see this, and it all kind of makes sense. And then if it's not getting too complicated, I'm so much looking forward to do this actually again. And I do know there will be another session where we go into this topic probably a little bit deeper and speaking a little bit more nerdy talk. And this session will be October 20th, if I'm not mistaken. And we would be all very happy to see you here again. And if there's nothing more inside the chat, I would say we call it a day. And thank you, Sebastian. It was it was very interesting. It was super cool. Thank you very much.
You're welcome. I hope to see you all again.
See you next time.